conformal field theory, like Alexei Davidov, this will not be possible because we have not thought that far. We come more from a tensor categories algebraic point of view. But the broad motivation is to move away from well-known stories of monoidal categories or tensor categories to monoidal 2 categories. So there are, of course, all of these well-known stories when you have, let's say, fusion categories. There's construction of invariants of links. There's constructions of 3D manifold invariants, ultimately 3D TQFT. And well, moving away from this, there's been a lot of development going to monoidal 2 categories. So this is most developed in semisimple case, where you have, there's now a theory of fusion 2 categories. And this is motivated by the pursuit for construction of 4D invariants. Now, both of these stories are very much semi-simple. Like you work with fusion categories where you have semi-simple tensor categories and you need to know the fusion rule. And here also in the fusion 2 categories, the story is very semi-simple. It's fast developed, work of Douglas Reuter and others since. But what Azat and I are most interested in is moving away from semi-simple. We're more interested in non-semi-simple tensor categories. And from that sort of point of view, we ask ourselves the question, can we find some concrete example of a monoidal 2 category, which is in some sense non-semi-simple? So maybe at this point I should say something about 2 categories. Like 2 categories are now, instead of having categories where you have objects and morphisms, we have a second layer of 2 morphisms between morphisms. Or in other words, if I have such a monoidal 2 category, it's denoted also by C. One has form in C between 2 objects, it's called an M and N. This is actually itself a category. This is, of course, not the weakest notion of 2-dimensional sort of category structure. You can also have bi-categories, but this is still a category, but composition is not really a functor. Here, composition is proper functor. And yeah, then one also wants a tensor product on such a 2 category. So there's some sort of tensor product. But this in general is not a functor. It's something called it's a very lax version of a functor called a pseudo-functor, which means that here composition. So composition, this is not necessarily a functor strictly. So there's always some sort of structural isomorphism that describe how taking these tensor products compute with composition of 1 morphisms. So it's a weaker structure. And we inquire to write on some concrete example that is not captured in the framework of fusion 2 categories, how to construct them, but in such a way that it's actually manageable. You can actually write some list of all of the objects. You can classify something. So many constructions of a monoidal 2 categories known from the literature, they're huge. You have no chance of classifying anything. We want a more concrete construction where we can understand everything. So this was the starting point of this project. And the way this is done is ultimately, we don't do a lot of 2 category theory. We go back to something that is in the world of tensor categories and well studied, which is module categories. So some sort of theory of modules, or if you like, representations of a tensor category. So I want to talk a little bit about module categories, how they come into the factor into this project. So here, let's give this some sort of bigger symbol. So this monoidal 2 category C, this is sort of, we now go back to an ordinary tensor category. So this is a tensor category. And by this we mean it's not an arbitrary monoidal category. There's certain assumptions to it. So this is, here we want to have duals, so it's rigid, like this was already mentioned in previous talk. It should be linear over some field. And homomorphism spaces should be nicely finite dimensional. So in particular, the tensor product will be exact. So these are well behaved. There's a finitely many simples. So these are well behaved tensor categories. And basically like the type of tensor category studied in the book by Ettinghoff, Deligne, and Ostrich. And we also want that the tensor unit is a simple object. So list of assumptions on these. But now there is a sort of a nice theory of categorical modules. So here left C module is now a finite abelian category. So maybe importantly, I didn't mention these categories should all be abelian. So you can think of these as fusion categories, but they're allowed to, of course, be non-semisimple. We want to move away a little bit from just studying the fusion case. And then such a category can act on a finite abelian category. Call it M. And now the action itself is some kind of functor. But now in this setup, because it's categorical, associativity is not a, of the action is not a property, it's always data. So you have some sort of coherent natural isomorphisms that tell us how to relate acting separately with two objects to acting with their tensor product. So of course, if we think back at representations of algebras or groups, this is just an equality, but here it's structural data. And sometimes this is also the only data you have. The functor, yeah, the action might be quite trivial, but then this data sort of captures all of the information about the module. So now here again, there's sort of three layers of structure. And it's going to be important for the talk that we also have functor categories. So we have something like, and for technical reasons here, we want right exact at this stage. C module functors, maybe called G, between two module categories. Here again, these are some functors, but they have some structural data, which is very important. There's some isomorphism that relates to the action and the application of this functor. So I can, if I act with an object X, I can move it past the functor G to some structural coherent system of isomorphisms, which again is part of the data. And of course, these data satisfy some conditions, some equalities of multiple application that should be related. In fact, anyway, you can like cook up, if you had several objects acting, there's some sort of coherent statement here, like for monoidal categories, it's all works nicely. So this is these are coherent systems of isomorphisms. And then there's a third layer here of C module transformations. Which not just any natural transformations, and natural transformations which satisfy a commutative diagram with respective isomorphisms, moving action past the functors. And but at the end of the day, what is important here is that one gets some sort of two category. It's a two category, which we call C mod. So this is two category of C modules. This is a well-known structure. And but we are interested here in looking at monoidal two categories. And this C mod is in general not monoidal two category. Like there's no tensor product on this naturally, but if you assume that now that C is also braided, so we have these structural isomorphisms commuting a tensor product. So some sort of analogy of commutative algebra. So you can form a similar tensor product. And there is this relative linear product or balanced product sometimes, which is somehow relative over C. So what does this mean? If I take two C modules, I can form their relative product. And here we should think about this the following way. This is some sort of categorical quotient of just taking the product of M and N directly, like done in Davidov's talk. But where here, because of the braiding, you can turn a left action into a right action. Kind of like for commutative algebras, if you have left modules, they also right modules, as the algebra is commutative. Here, the braiding can, right, with some choice made, turn left actions to right actions, so you can identify commuting the action from one factor to the other. So I'm not going into a lot of detail here, but this is a universal construction where you can form this relative Deligne product, which sometimes exists actually in large generality. And one can show that because it's a universal construction, you can find some kind of associators for this product. But associators are here functors, so you should not compare them up to equality, you should only compare them up to isomorphism. So there's always an additional layer of structure here, but at the end of the day, what one can do here is one can form monoidal two category. So for this to work properly, there's a few things that are important. I mean, what is important is that we work with finite abelian categories. It's also important that our functors are right exact. It's actually important that this action here, the tensor product, the action is also exact functor in both components, but these are just very technical details. So in a nice setup, one can make sense of this monoidal two category, and it's kind of quite well known that this exists. It's a sort of a source of monoidal two category. And if C itself is not semisimple, then this is not semisimple also. It's just a very general construction. Of course, this is somehow, I'm not sure if I should call it an issue, but this is a very, very large category. If you even special case, we might go very, very basic. What's the easiest tensor category we know, but it's finite dimensional vector spaces over some field. If you look at finite dimensional vector spaces over some field, maybe the easiest tensor category you can imagine, in fact, the easiest. Then sort of classifying objects inside of A mod is equivalent to the problem of classifying finite dimensional algebras up to Morita equivalence. Morita equivalence meaning they have equivalent categories of representations on modules. But this is a wild problem, and this is not a traceable problem. We can't just go about classifying all finite dimensional algebras. It's done for semisimple, of course, but in non-semisimple cases, this is a huge universe, it's a huge ambient category, which works for abstract reasons. But if we want to construct a monoidal category where we know all objects, we know what functor categories look like between different objects, then this is too large. So here's how the story continues in a semi-simple case. Most literature, I mean, in this field, monoidal two categories, but also even just tensor categories and their modular categories, mostly first done in semi-simple cases. It's a stronger motivation from mathematical physics. It's also easier case maybe to work with. So this is what people start with. In this case, we can pose well here for vect. For C, for vect, if I just don't consider all modular categories, but the semi-simple finite ones, the problem will be quite managed. So if C is a fusion category or braided fusion, yeah. Let's also say here that characteristic of A is equal to 0. Then we might just consider semisimple. C-module categories. And then in that case, a phenomenon that was shown, I think because certainly such argument can be found in the book of Gainutdinov and et al., that there are finitely many indecomposables in C-mod. Let's give it some superscript semisimple here. There's finitely many, and if you go to this easy case, it will be classification of, but I guess this is, let's say, in addition here, maybe that the field is algebraic because really make it easy. If you go back to this case, you see, well, there's not so many semi-simple algebras of monoidal equivalence like this. Martin Wedderburn's theorem tells us that you just have a product of matrix algebras, but all of them are matrix algebras equivalent, monoidal equivalent to just the field itself. So there's really not much going on. There's only finitely many indecomposable ones. Okay, so now what else has been done? So in slightly more generality, if some of these assumptions don't hold, for example, characteristic is actually not equal to 0, then there's a concept of a separable module category, probably due to Douglas, Schomerfree, Snyder, but also used later in this work by Douglas Reuter on fusion 2 categories. And so you can consider separable C modules. C-sep. And again, this is quite finite. There's many indecomposables. And this is closed under the tensor product. So both of these classes are closed under this tensor product. So this is a way to get a fusion 2 category. There's other ways to construct fusion 2 categories, but this is already a large class of examples. Are there any questions so far? Okay, so we now wonder what to do if we're not in semisimple case. Yeah.
Fusion are they the same? For fusion, are they going to be the same?
Well, if the characteristic is 0, or you have more technical assumption on global dimension of the tensor category, then they do agree. So somehow this is this like generalization that will also work in bad characteristic, in positive characteristic. Okay, but now we're interested in non-semisimple. And there's already something. So there's this notion of exact categories. This also, I think, is due originally maybe to Eating of Ostrich, paper on finite tensor categories. And exact modular category M has to satisfy certain property with respect to projective objects, which will ensure that the modular category, that these modular categories have very, very good homological algebra feature. Basically, homological algebra will become quite trivial for exact modular categories. So what does it mean? It means if I take P to be a projective object in C, and then I take any object M in the module M, so just any object, then it's told for M to be exact that P acting on X should be a projective. So I can pause for a moment to think about semi-simple categories. In semi-simple categories, all objects are projective. So this, and if then the module M is semi-simple, right, the condition becomes trivial because every object is projective.
It's M, not X, right? Or
oh, this is the yes. Yeah, we need to act on M, right? We can't act on X here. So yeah. So for semi-simple categories, the statement is so C is fusion. This is not possible. So C is fusion, semi-simple. Then one can say that M is exact if and only if M is semi-simple. And an important feature here is, I'm going to state maybe a more general version, but I think it holds as soon as one of these two is exact. So if you have two exact, then if you look at the functor category from M to N, every object or every functor is exact. So in general, previously we just wanted right exact functors, so the constructions work, but if the multicode is actually exact, then every functor will be exact. Maybe this is where the name comes from, but in particular, this is good because it means somehow you have left and right adjoint for each functor. This is also quite a strong assumption. It will vastly restrict the class of our module categories if you just look at exact.
So what do you think on C? C is for that statement. Do you assume something?
Yeah, we just look at finite tensor.
Just finite.
So for the last line, it's not fusion, it's just any finite tensor.
Yeah, finite tensor. Yeah, so that's somehow there we go back to finite tensor. Okay, so now the problem we encountered here, if M and N are exact, two categories, let's say again. So I still want to work C, just finite tensor category B. We're not in a specific case. Then this may not be exact. So this is a problem we encountered when we wanted to study this. Maybe first a comment. So exact indecomposable module categories, they're actually classifiable and they exist results to classify. It's also initiated maybe by Edinburgh and Ostrich, but Martin Momberli also provided some classification results for a certain interesting type of quantum groups and the representation categories of indecomposable exact module categories. This is something manageable. It's maybe infinite set, maybe continuous set, but it's classifiable. So it's a much, much smaller class. But the problem we face is we want to build monoidal two categories, so we need this relative Deligne product to also be exact if we wanted to have closure, if you have some sort of monoidal category. And this fails sometimes. And maybe I can try to give an example at this early stage. But at this early stage, I think easiest example is explained, I think, in characteristic P. So we have also counterexample in class characteristic 0, but it's a little bit harder to state. I'll come to it later. So let's go characteristic K equal P a prime, but such a prime that divides the order of the group G, where G is a finite real group. Now in this kind of situation, we can look at C, just vector spaces graded by the group. So here vector space just has some sort of group grading into components. And this is always a semi-simple category. Simple objects here are one-dimensional vector spaces, where the one dimension is just concentrated in one of the degrees. So for each element of the group, you have a simple object. This is a finite tensor category. And because G is abelian, we can even make it symmetric. Tensor category. But now, what kind of module categories exist? Of course, every tensor category can act on itself. This tensor product, this is always the monoidal unit of this operation of relative Deligne product. But here we can take sort of categories of vector spaces. This is a category of vector spaces, there's natural categorical action on it, because because we have a fiber functor. We can go back G. It's a tensor functor that goes to vector spaces where you just simply forget about the gradient. This is a tensor functor. And now, what do we know about this? Well, we know that it's known what is the category of all endo functors. This category becomes equivalent. This is a statement, for example, in the tensor categories book. The categories of representations of G. But now, because this is bad characteristic for the group G, that means that this category is not semi-simple. Okay, it does not explain to us much about tensor products just yet, but in fact, there is a sort of an inner Hornmore type of representability statement that tells us that this category is actually equivalent to a relative Deligne product of some kind of dual. So the statement is an analog of well-known fact that if you look at, say, maps of modules and you have a dualizable representation, you can write the space of all A-linear maps as some sort of relative tensor product, or more easily in vector spaces, linear maps are some sort of tensor product of the dual and the object itself. So here, so this I should credit to Douglas, Jean-Marc Snyder again in the monograph. They also show the following result. They show that if M is exact in the above sense, it will imply that this M, this dual, is also exact. Now, what I haven't mentioned here is that of the category of vector spaces, of course, is exact. Because this is a semi-simple category. So this condition here. So we defined exact C module category. It says that if you take a projective object of C, well, every object in C is actually projective. You need to act on any object is to give a projective object in M, but of course M only has projective objects. Every object is projective. This condition is empty. Because M is semi-simple, it's exact, its dual is also exact. So, but here this category, because it's not semi-simple, it's not exact. It's C module. Now, here, of course, I have a valid question to ask is how is this even a C module? It's sort of not really explained here, but because of the braiding, you can produce C action on functor, C linear functors. It's possible because we have a braiding. And then this shows that there's in general a difficulty with this relative Deligne product and exact module categories. And this is, I think, this is the motivation for our work. So. Any questions at this point? Okay, then I want to give some definition. So now let's get to actually the topic, fully exact. So again, we take C. C again is a finite braided tensor category. This entire series is not valid for C not being braided. So somehow the series is a series for braided tensor categories and module categories at the moment. The sort of general definition can be, I think it's relatively clean, but it doesn't tell us much. So we can say that left C module M is fully exact if it satisfies the following property. For any N which is exact C module, so here I should say that I'm always looking at left C modules here. So if I take any exact left C module, I want that N tensor over C with M is also exact. So I want to just specifically look at such left C modules. These are not necessarily exact themselves, but from the definition it will follow, for which that somehow if you fix this M and you act on the right, on a set of all exact modular categories, you have closure. You stay within exact modular categories. And then maybe some remarks. First of all, this definition implies that M is exact. If we use N specifically to be the sort of tensor unit of the monoidal 2 category of finite modular categories, then we see that there's some equivalence of tensoring on the left C with M, so M itself also has to be exact. Then another trivial observation is that fully exact, so that the unit itself, C, is fully exact. And here, of course, we do this the other way around now, because we have N, tensor C is always equivalent to N. So if N is exact, then of course, this thing is also exact. So we have a unit. This is the first example. Now, we have paid some attention to Hopf algebras, and tensor categories arising as representation categories of our Hopf algebra. So, or maybe before I say that, I should make a remark here. So if C is semi-simple, and we also have the characteristic of K is equal to 0, then M is exact if the anomaly of M is fully exact. From this diffusion case, there's no difference. It's a non-semi-simple phenomenon. And then sort of we study examples that we look at are module categories for Hopf algebra. So H is a Hopf algebra. The quasi-triangular Hopf algebra. Then you can see sort of vect K is a C module. And this C module vect K is often I'm not quantifying here at the moment, but not fully exact. So here we can nicely analyze when this vect K is actually fully exact and when it's not. It's a condition on the R matrix. A quasi-triangular Hopf algebra would have an R matrix. And whether or not vect K is fully exact is a condition on the R matrix, which I could make precise, but I'm not sure if at this point.
Should relate to the braid, yeah.
Yes, related to the braiding, so maybe make it precise over here. So if you have this R matrix, you can use it as follows. Also, like, let's say I write diagrams from top to bottom, so I apologize for that because I think it's common than the other way around. But for the R matrix, here's an element of H tensor H. So we view it as element of H tensor H. So it's a string written as some sort of diagram. Here we can, okay, I think I'm confusing left and right. I want it this way around. So let's start here with the dual of H star. We can use evaluation pairing. And this way we produce a map. This is a map that goes from, it's a map by phi R. It's a map from H star to H. It's very sensitive to the braiding. For example, if the braiding is trivial, it could be a symmetric, triangular, not even triangular, co-commutative Hopf algebra give R just equal to 1 tensor 1. In that case, this morphism factors to the co-units, the factors to K. It's definitely not an isomorphism in that case. And then let me change this. So this vector is fully exact if and only if the restriction along this map. So restriction along this map is a functor from H naught to H star naught. And this functor preserves projectives. So you see, this is a The morphing goes from H star to H, and the restriction functor along it will go from H modules to H star modules. And this should preserve projective objects. But if, of course, H star was semi-simple, then every object is projective, so there's no condition. But if H star is not semi-simple, like in this example over here, then there is some sort of condition. So we can actually use this to verify the example up here, because here we use group algebra, this trivial R matrix, 1 tensor 1. Or actually, I should use dual of. Technically, you see the dual of the group algebra. And then the morphism factors through K. But the target is not simple, so cannot project preserve projective objects. Any questions at this point? No, it's actually now easy to see from the definition that we get monoidal two category. So this can now be, I don't want to call it alias here, more like the composition. Because this is also coming up in this work. It's Azat. So I will call CFX so the two categories are fully exact multi-categories. So all of the objects are fully exact multi-categories. We use the same functor categories as in mod. So this is in the monoidal 2 category. Because if we examine the definition, you have definition is that M, if you tensor on the left with anything exact, you should always get something exact. But if I now use M1 tensor M2 on the right, I can re-bracket and see that M1 tensor M2 should also be fully exact if M1 and M2 are fully exact. So this is the source of monoidal 2 category. And the theorem we have is the following: if C is that M be finite category, the following conditions are exact. First, M is fully exact.
Yeah, all conditions are equivalent.
The following conditions are equivalent. So you don't.
You said exact.
Oh, I said exact. Okay, yeah. No, the following conditions are equivalent. Okay, so first M is fully exact according to the definition, and then second, so there's something we call action functor, but this is also called alpha induction. Specifically in papers like paper by Davidov-Niksic, it's the action functor alpha plus. There's somehow two alpha induction functors, alpha plus and alpha minus, and the theory is sensitive to which one we use. But the alpha induction functor goes like this. It goes from C to end. So this is the category of all endofunctors. This itself is a monoidal category. It's called C star M in the book of HMO, and it's called the centralizer. And the centralizer plays quite an important role in the module theory for finite tensor categories. There's some sort of Morita equivalence between C and C star M. So this is an important construction there. But the condition here is that this functor preserves projectives. And then one can write third condition, which says that I briefly talked about this dual earlier. So this category tensoring dual with M is exact as a C mod. three potential and three equivalent conditions.
Is the dual of a fully exact C-module category fully exact?
In general, not, but sometimes it is. Yeah, I'll comment on that later. That's an interesting question. So here we find some sort of monoidal 2 category. And this bigger monoidal 2 category of C mod, it has duals. So this dual, I just don't think I wrote a formula for it earlier, but this n star here. Well, there's a left and a right dual, but in this talk I only focus on right dual. It can be defined abstractly as C linear functors from M into the unit. This looks very similar to vector space dual, where you just map it to K. There's also construction of, well, it definitely features quite a lot in Douglas, Schomerly, Snyder's monograph, where they show that this indeed is a categorical dual. And you also have a left categorical dual. Now, so I will comment maybe on dual later if I have time. So in general, dual is not always fully exact, but I wanted to actually present some example in a little bit more detail. I think it's nice to have some more concrete example. So now, when we want to find an example, we ask ourselves, what is the easiest non-semi-simple finite tensor category that we can think of? So it has as few objects as somehow possible to get something Sweetler. Yeah, exactly. So we take S to be Sweetler Hopfalgebra, it's 4-dimensional Hopfalgebra. Maybe we do over complex numbers. It doesn't matter, but it's completely sufficient for purpose. So this gives a 4D Hopfalgebra. This is very nice. Its representation series is finite. There's only 4 indecomposable modules. There's 2 simples and 2 projective covers of the simples. There's 4 indecomposable modules. So this is and it's non-semi-simple. So then I'll define C to be S mod. Non-semi-simple. So we have such nil potency relation. This can otherwise not happen really. And we need to produce a braiding. We need to work with braided category. There's different ways of doing it, but all of the braidings is symmetric. So let's choose for the moment, basically braiding inherited from category of supervector spaces. So we can use R matrix. Minus G tensor G. It's a symmetric braiding. So now there's a classification of indecomposable exact module categories. Now it's to a credit. So this is originally mentioned in eating of Oxford, eating of, yeah, I think, or ENO. But this was also done very more generally, and also this sort of classification that actually these module categories appearing here are not actually equivalent by Monbelli, maybe 2006. But there is the following list of indecomposable exact module categories. Of course, we have C itself, we always have C. Then there's some other slightly more mysterious category, which is, I want to write it heuristically as X modulo X squared mod. So this is non-semi-simple. This doesn't explain the action, but it's non-semi-simple. So these are the 2 only non-semi-simple indecomposable exact module categories. But there's a lot of semi-simple ones. We can call that lambda and S lambda. Here's a complex number. Now, what does this mean? Vect with lambda equal to 0 is just category of vector spaces with natural action. But you can twist the fiber functor, the forgetful functor, by certain tuple cycle in the family of tuple cycles parameterized by a complex number. And you can do exactly the same thing with the Cardiac vector spaces. So you can also act on Cardiac vector spaces. So these are two parameterized families. And now we have the proposition. We have that CD vector lambda, S vector lambda. The lambda is not equal to 0, are fully exact. And we have that vect 0 and S vect 0 not fully exact. So this is, so most of them are fully exact, which is good. There's a continuous spectrum of fully exact. But there's some exceptional points which are not fully exact, and this was the Deligne tensor product. And then one can also compute, and here we use some results of, I think, Azat and Christoph Scheiger's former PhD student Laugwitz thesis in order to do these calculations. But then we get that we cannot compute what are tensor products. So I want to, in order for this to make more sense, define V lambda to be vect 1 over lambda equal to 0, and then S lambda to be S vect. And then we set specifically S0 to be this category D, and V0 to be this category C. There's somehow a reparameterization of the families. We take out the 0 point because we can't take 1 over lambda in this family. Somehow vect 0 would correspond to point at infinity in the family. But that point is not fully exact, so we don't use it. But to make a nicer formula for the tensor product, we parameterize here, and then one can compute. Something like the lambda tensor v nu will be equivalent to lambda plus nu. And well, I somehow did not time here very well how to use the board, but if you tensor together the s's, you get a v. So somehow S vect tensor S vect becomes vect, but the same relation on parameters. And if you have mixed, vect v tensor S will always be S for sum of parameters. So. And it's also symmetric, so this monoidal two category actually ends up being symmetric. And this formula extends to 0, so if lambda is equal to minus mu, we get S0, so we get non-semisimple outcome tensoring together two semisimples. So somehow this all looks, it's Z2 graded. Somehow this product appears to be Z2 graded. Any questions at this point? Okay, then maybe because there's not a lot of time, I want to
12 minutes.
12 minutes, okay.
Because we started late.
Okay, so maybe I will comment briefly on duality because it's I think interesting, and then make some comparison to other classes of module categories that are also close on a tensor product that people studied in the literature, such as invertible or separable module categories. So let's think about duality. So before it becomes apparent, I want to sort of, the question here is, I'm fully exact. Let's look at the dual. But is it also fully exact, or is it maybe something else? And in order to explain what it is, so I have erased at this point, but the definition of fully exact somehow was used certain choice about left and right. By the fully exact, we said that we take M and we tensor M on the right with any exact, and we should get exact. But why did we not tensor on the left? So there was somehow a choice made here with left and right. So we can define an opposite action, opposite notion. So we say, so finite module M is not fully exact. If I take any exact modules N, and if we take M now, tensor on the left here is exact. So this is, again, it's actually important that we work here with left. This is why we didn't call left-right exact, because we specialize already to left C modules. But one way to interpret this is saying it's somehow it's fully exact for opposite monoidal product. So we reverse in the definition of fully exact, we had M tensoring on the other side, but it tensors here on the left. So this is the opposite somehow notion in terms of tensor product. And then one can show that M is fully exact if and only if dual is off. Or maybe it's better to actually let me put a dual. Dual is fully exact if and only if M itself is not fully exact. So somehow the dual leaves this class and goes to a slightly different defined class of fully exact, not fully exact. But sometimes the two notions are the same and sometimes they're not the same. So one proposition we can show, it's not too difficult, because if C is actually symmetric monoidal, then C mod is a symmetric monoidal two category. So you have isomorphism left and right tensoring. So of course, in that case, maybe it should be called a corollary. If C is symmetric monoidal, then M fully exact. Only if stars fully exact. One can also have similar results, a little bit more specific to M. So if M is given by internal modules of a commutative algebra, then it's fully exact, if only if fully exact. Or if M is something called braided module category, which we will not go into, but it's then also the two equivalents. Sometimes two notions are equivalent, but there's also counterexample. For the example of something that is fully exact, not fully exact, we go as far away as possible from symmetric. So we go to factorizable case of a Drinfeld center. C to the Z of D, and now D is KG mod or web G, let's call it web G. Again, G is finite group. And here, we again, to make this counterexample work, we don't know counterexample characteristics 0, but we wanted a characteristic of the field divides the order of G, which makes this non-semisimple category. And then, right, because this is equivalent description here is to say this is the Drinfeld double of the group algebra. So modules over the Drinfeld double of the group algebra. This is the Drinfeld center. Because that's a Hopf algebra, there's again fiber factor to vect. So we can take M to be vector spaces in module categories. Sort of one of the first examples one might want to consider. And then M is fully exact. but not op fully exact. And the reason this comes about is because full exactness of vect we saw depends on some property of the R matrix. And for the dual, it involves inverse of the R matrix. But because here in the Drinfeld double as a vector space is defined on Kg tensor its dual, one of these algebras is semi-simple, the other one is not. So somehow, depending on whether you use here R matrix or inverse R matrix, you get a different outcome of observing projective objects in the restriction factor. So in general, we have to be a little bit careful. We can't just say that fully exact is stable under duality, but sometimes it is. Or we want to actually, then we can consider some sort of category of fully exact D, fully exact, and of fully exact. See how it is. So this is nice because here this category is stable under duals. Also in such category, every functor is a left and right adjoint. So this category has a lot of dualizability. Objects have duals, one morphisms have duals. Some people might call fully dualizable the objects in such category. Okay, so this is basically a brief comment on dualizability.
Ym is, so this first example, Ym is fully exact.
Okay. So here we consider R matrix, and sort of doing this on the spot, I might mix up my conventions a little bit, but R matrix here should be element of DH tensor DH, or DG tensor DG. So it's and the tensor product of Drinfeld double. And how is this set up? Maybe here we use group algebra and here we use dual. Or maybe here we use dual. Let's use dual group algebra here in this tensor part. Here we use the group algebra. This is roughly what our matrix of Drinfeld is. Okay, so what we had to do is we had to consider, as mentioned previously, a morphism from H star to H, where H here is algebra, induced by pairing up, by applying this R matrix and using some pairing. So
it's also alpha induction, right? It's just alpha induction.
yeah, alpha induction is restriction along this functor. But now the way you set up here, I mean R inverse, and now of course this is something okay, I would have to look at the notes, I guess, or the draft, but how does it work? I think it uses inverse antipode, but otherwise looks very similar. But I think it also swaps. So yes. Now inverse, no, that's right. Inverse of the R matrix just applies antipode to one of the outputs. I think it does not matter here which one because it's all very commutative. Well, it doesn't have to be commutative, but it's all very co-commutative. So we have to also use inverse R matrix, but with a swap of component, because if you want an inverse to be an R matrix, you have to swap the two components. So one of these morphisms has.
So in terms of alpha induction, would be the other one just alpha minus?
Yes. So one is alpha plus, alpha minus. Now, for one of them, and they're both factors through tensor unit on one part of the Drinfeld double, but not on the other. So let me see if I can get this right on this one. So I think here I'm drawing the one for R, and this part here is the dual start point. This is Kg. So The image of this morphism is K, G star. And here it's just somehow trivial, this is somehow pivotal structure of vector spaces. I think here we need, sorry, this is, okay, we go to the dual. I think this is KG double dual image, KG star. So I mean, modulo details, one of these morphisms has the image, the semisimple Hauptalgebra, the other one has the non-semisimple Hauptalgebra in the image. So one of them will preserve projective objects just because the parted factors to the tensor unit is semisimple Hauptalgebra, doesn't matter. For the other one, it will not preserve projective objects. This is roughly the idea. So we play heavily on the fact here that that's a Hauptalgebra where the dual is non-semisimple, but Hauptalgebra itself is not semisimple.
HH star not symmetric.
It's non-symmetric in that sense.
And they've swapped, so
It's also what made it sort of, Mr. Looking, for example, and things. You can see like characteristic 0. But to finish briefly the talk, I just want to draw a diagram and comment on some other notions. In fact, he also suggested you should think about invertible tensor categories. So there are two other categories one can consider: separable and invertible. See modules. So what does it mean to be invertible? It's very similar to, of course, invertible elements of a group, but here we have a two category. So M is invertible if it exists some n, such that M tensor n is equivalent to C, and also n tensor M is equivalent to C. So simple notion of invertibility as of an object in two categories. And this becomes two categories. Separable means that M is equivalent to right modules over some internal algebra. But and here there exists some A which is separable algebra internal to C. So what this means that the multiplication has a section as a bimodule map. Means if a multiplication of the algebra is this sort of map here, there exists some other map, call it delta, such that the composition is equal to the identity on A. But this map doesn't have to be a coproduct, and it's just a map of morphism of bimodules. So this is something like separable Frobenius algebra. And if for some module category M you can find such separable algebra, you call such module category separable. And this notion is also closed under tensor product, and it's closed under duals. In fact, this is heavily used in semisimple case. In this literature on semisimple module categories, they use this concept because it's closed under tensor product. And you get problems if you just require semisimple. Now, inside of here, we have fully exact module categories that are closed under duals. So these are fully exact and not fully exact. And then here, we have separately monoidal two category of fully exact and not fully exact. Of course, all of them are contained in this huge category of C mod. So these are all inclusions of monoidal two categories. At this point, you start having duals. So here we have duals, simply by assumption. And these also have duals. And here for invertible, you have duals, like the inverse is a dual of n. So this is the bigger picture. So invertible separable fit into fully exact, but then these are not equal. In some example for Sweetler,
Say that fully exact have duals, but you also have this proposition that
no, it's CFX with D.
sorry.
CFX with D, it's fully exact, which are also fully exact.
Oh, that's D. Oh, sorry.
Yeah, see they contained in two.
That's why
Contained in both.
otherwise duals will be.
Yeah, just maps just
Yeah, otherwise dual will switch between it.
So there will be an equivalence, right?
Yes. Yeah, double dual is an exact sum. Even if you don't have ribbon, in general, this double dual is.
As what C is just braided
Yeah.
finite, it will be automatic that it's vertical.
Yes. If you have ribbon, it happens that M and MW are actually equivalent, but it's not necessary. Right? It's just that going with M, going to M star, going back here is M double star, they provide equivalences.
So you're saying that it doesn't have to be isomorphic to M double star is not automatically isomorphic. So
I don't think so. No, not in
so you
general.
have just not equivalence on this on each of them.
Yeah, at least we're not sure if you have an example, but I don't think it's true. If you have
Pivotality would
maybe
be next.
pivotal is actually enough. We'd have to think about it. Well, you have braided anyway.
In symmetric case, I think they are, right?
In symmetric case, there are yes.
Yeah.
Symmetric
Because
case,
even if it's just on braided, not symmetric category, I don't see why it should be isomorphic. It's a condition on the category.
you can exactly ribbon structure will provide equivalence between M and MW.
Ribbon structure on C.
Ribbon structure on C. Yeah. Okay, maybe as a final side note, if you again take S mod for suite algebra, then C inf separable just contains C and D, or which we also call V0 and S0.
Nothing more.
Nothing more, just two. So it's basically categorized somehow Z2, but there's more. There's these infinite families. They're not shouldn't be separable. Yeah, but invertible. Interestingly, here all of indecomposable fully exact is also invertible. But if you go to other examples, even group algebra, I think this fails. Then, in general, of course, not every exact modular category is invertible, even in fusion case. So these classes are different. So this sits here is not sort of by coincidence equal to C. It's strictly large in general. Okay, I think this is all.
Sure. Thank you. Other questions?
You mentioned braided module categories fit into your corollaries.
Yeah, but I mean, we don't do much with it here, but I mean, I think it's the result of Davidov-Nitzig that having a braided module category corresponds to the datum as a monoidal isomorphism between alpha plus and alpha minus, which are two alpha induction functors. For us, alpha plus measures fully exact if it preserves projective objects, alpha minus measures op fully exact. Of course, if these functors are isomorphic, then they will preserve projectives at the same time. Therefore, braided module category is fully exact if and only if op fully exact, but of course it is not clear that a braided module category should be either. So braiding on a module category does not help to make it fully exact, I think. But if it is, then it's also op fully exact. Yeah.
That would happen is if C is not a finite tensor category, but something, for instance, like a GV category.
We have not gone this direction. No.
I mean, that's
First
the
question.
notion of GV module category, for instance.
First question. Yeah, it's an interesting question, but you first have to investigate whether relative Deligne product exists, or maybe replace it by Kelly relative product, just to check if that actually exists in the same class. So I think this fundamental question probably not known for these generalizations. Yeah, but here somehow the groundwork, at least it's a very folkloric theorem that is one of the two categories.
Right.
Many authors have stated this theorem.
Yes. Are there any questions?
Yeah.
In the very beginning, you restricted to right exact functors. Is this to guarantee existence of the relative Deligne product?
Yes. Yeah. So what it helps us as a technical tool, which is not much in the background of this talk, is that we work with internal algebras. The module category M can be expressed as internal modules over some internal algebra in C. This is also a result in the EGNO tensor categories. But then if you look at functor categories, you want them to correspond to bimodules, internal bimodules over your algebras. And this is an Eilenberg what theorem. It says that right exact functors will correspond to binaries. So this makes the categories of right exact functors much more manageable. Otherwise, they're too large and you can't work with them. If you don't require at least right exact functors, the categories just become too large. You cannot work with them, and I don't know if it's monoidal two category. But even for forming relative Deligne product, it's very natural to look at right exact functors.
So by looking at this example here, do you have any intuition behind why twisting this associator will play a role to change this fully exactness?
Well, yeah, there's some understanding of maybe it's too. So if you twist, if you start with vect and you have any sort of J, which is a 2 cocycle of H, then you can twist vec to vec J. The fiber functor can be twisted by conjugating with a 2 cocycle. In that case, somehow has the effect of changing this VR to V of phi R twisted by J, which changes the R matrix. So, I mean, this is not 100% the full story, because I think somehow move away from strict modular category here to less strict modular category, but essentially this changes the morphism that is key to determining fully exact. And in Sweetler case, you can, interestingly, in Sweetler case, you have a lot of ratings on the same category. And for some of them, sort of morphism is the R matrix. This might be an isomorphism for some other choice of R matrix for Sweetler. If you take R lambda, this could become an isomorphism. And then if that's an isomorphism, that means the corresponding natural action on vect is invertible modular category. But for lambda equals 0, it's not an isomorphism. So somehow the twisting changes that morphism. So somehow maybe a better thing to say is to say that no, if you just look at a modular category over C and C doesn't yet have a braiding, and then you go and study all of the braidings on C, then fully exactness is sensitive to choice of braiding.
So lambda 0 for V is C, so that should be invertible, right? You say that lambda is 0.
Different dimensions.
Okay, so I did a little switch here in between.
Okay.
Here it's inverted, yes.
So it's lambda inverse, okay.
We invert the parameters. And then we artificially set V0 to be C. But originally, vect 0 is just vect. That was the non-invertible one. Yep.
Yeah, that is with infinity. Similar.
Modular categories to be finite.
Can you speak louder? Mati, can you speak louder, please?
Yes, so modular categories which are exact but not fully exact, do you expect that family to be finite in general, or do you have examples? Because here you only have 2 cases, right?
Is here it's just 2?
But do you expect this to be finite always, or
What finite?
the family of modular categories which are exact but not fully exact?
Good question. I don't know. We have to.
Yeah, we don't know.
I mean, like the examples we have, it's finite, but no, I'm not sure. I mean, I think if you go higher dimensional exterior algebras, I expect it's not finite.
Okay.
It's just feeling. I don't know, but we need to work more.
Yeah, maybe also a point, like, of course, here naturally, sort of by construction, exact is some sort of categorical bimodule over fully exact. 2 categorical bimodules. Like fully exact is constructed, so you can always tensor on your state as an exact.
Yeah. Seems no more questions. Let's thank Robert again. Thank you. It's not time for lunch. We'll be upstairs in the cathedral.